right?
In geology, as a geologist. So I wanted to go into planetary geology for a while, and then said, no, astrophysics is the way to go. I went to Wyoming for his PhD. At the time, Wyoming had the largest infrared telescope, so you know there. And then moved to the Smithsonian in Washington, D.C., and then arrived at NASA about the same time that I arrived here at Brown, and spent his career JWST, and until recently was the Integrated Science Instrument Module Project scientist. Surprised it's not an acronym. So an interesting fact about JWST is it requires a lot of travel to get it together. So JWST is about 1 million miles away in an orbit beyond the moon, and to get JWST built, our speaker has traveled round trip to JWST.
All right. Great. If we could dim the lights in the front, I think it would help a lot.
Hit the second button from the top. One that says
Okay, thank you everyone for coming out to hear about the James Webb Space Telescope project. Now, traveling back in time is the stuff of science fiction. But looking back in time is something that we can actually do, and it works as a result of the finite speed of light. If you look at the person seated next to you right now, you are not seeing them as they are. You're seeing them as they were a few nanoseconds ago, because that's how long it takes light to travel 1 meter from that person to your eye. Now, a nanosecond is a really, really small amount of time, so that transmission delay is completely imperceptible to us. But when we look at objects that are farther away, the effect becomes more pronounced. For example, if we had a magic switch that could turn off the sun, and we flip that switch, it would be 500 seconds before we saw anything happen. Why? Because it takes light 500 seconds to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. If we look at the nearest star, we see it as it was 4 years ago. If we look at the center of the galaxy, we see it as it was 25,000 years ago, and so forth and so on. And so one of the things that we do with space telescopes, telescopes in general, is look back in time to understand the evolution of the universe. All right, the Webb telescope was conceived in the early 1990s to connect the dots, if you will, between this famous image and this famous image shown in an evolutionary context of this cartoon of the evolution of the universe. This image was taken by NASA's COBE satellite. It shows us what the universe looked like when the universe just became transparent. So this is an image of the oldest light in the universe. And these pink and blue blobs denote temperature inhomogeneities, which are the seeds from which galaxies will eventually form and evolve. At around the same time that COBE did this work, the Hubble Space Telescope was launched. And the Hubble Space Telescope took the deepest image that it was able to take at that time, and that shows us what the universe looked like when it was 1 billion years old. And between this epoch, studied by COBE, and this epoch, studied by Hubble, there is a very poorly studied epoch known as the cosmic dark zone. But that cosmic dark zone is poorly studied because we haven't had the right type of telescope to study it. But it is of tremendous scientific interest because it is the epoch in the evolution of the universe when the first stars in galaxies formed. And so studying that cosmic dark zone, making that available to science, was the original impetus of the Webb Space Telescope. Now, you've all heard the statement that space is expanding. This cartoon tries to show what is meant by that. Here you have a loaf of raisin bread dough that's been set out to rise. Now imagine that you're seated on one of the raisins. What would you see? You would see all the other raisins moving away from you, and even though you're not at the center of the expansion, and no matter what raisin you chose to sit on, you would see exactly the same thing. That's a good analogy for what we mean by space is expanding. We don't mean the galaxies are flying through space as if they was the result of some explosion, but rather the space itself is expanding. Well, what does this have to do with the James Webb Space Telescope mission? Well, we want to study the first galaxies in that cosmic dark zone. And those primeval galaxies emit their light in the ultraviolet part of the spectrum. But as that light travels to us through the expanding space, through that expanding raisin bread dough, its wavelength is stretched from the very short wavelength ultraviolet to the longer wavelength infrared. So to see that light today, we have to build an infrared telescope. And the infrared capability that we put into the Webb enables this science, but is useful for lots and lots of other science, as we'll see. Now, what do we mean by an infrared telescope? Everything that we know about the universe outside the solar system comes to all that information comes to us encoded in starlight. And the job of the modern astronomer is to extract the physics information from that starlight. Well, in order to get all of the information, we want all of the light. But all of the light doesn't reach the surface of the Earth, and all of the light cannot be detected by our eyes. Light comes in an infinite spectrum of wavelengths, from very short to very long. Only a very narrow slice reaches the surface of the Earth. And our eyes have evolved to match this little transmission window in the surface of the Earth. So this visible spectrum, as we call it, is the part that our eyes can see. But shortward of the violet end of the rainbow, we have the ultraviolet. Our eyes can't see that, but your skin could be burned by it if you stay at the beach too long. The Hubble Space Telescope is designed to operate across the visible and ultraviolet part of the spectrum. In contrast to that, the Webb telescope is designed to operate from the red end of the visible out into the infrared. Our eyes can't see infrared light, but your skin can sense it. If you hold your hand near a warm radiator or a warm stove burner and you feel the heat, that's your skin sensing the infrared light being emitted by the warm object. All right, so you can think of infrared light as heat radiation, and that's what JWST is optimized for. Now, the spaces between the stars in our galaxy, the so-called interstellar space, it's not a cold, empty vacuum. It's filled with giant clouds of molecular gas, atoms, ions, dust particles, and so forth. Here you have an object called the Eagle Nebula. This is a giant molecular cloud of gas in space. Some newly formed stars have occurred here, and they're pumping out a lot of ultraviolet radiation, which is ionizing the molecules of this cloud, causing it to produce this visible nebulosity. Now, early in Hubble's mission, it took a very famous picture of a piece of this Eagle Nebula called Pillars of Creation. So what do we have here? We have these filaments of molecular gas, and their filaments are opaque because they're mixed with dust grains. And this visible light cannot penetrate that dust. But when we look at this object in the infrared with JWST or any infrared system, the longer wavelength infrared light can see through the dust and give us a better vision of star formation action that's occurring in these clouds. And this is one example of how JWST will use its infrared capability to help us understand star formation close to home. Here's another example where you have newly formed stars occurring in this big molecular cloud. UV light is impinging on the cloud and causing the molecules to disassociate. You can see hydrogen streaming off into space. You have all these embedded newly formed stars. The one without diffraction spikes are still embedded. You have supersonic outflows occurring from that star formation, creating bow shocks of emission. Really rich things to look at in the infrared when you have the JWST's ability to see fine detail like this. All right, so we know the basics of how stars form. These giant clouds of molecular gas in space collapse onto themselves by self-gravity. And when the cloud collapses onto itself, the pressure inside the cloud begins to rise. And when the pressure inside the cloud rises, the temperature rises. It's very much like when you fill your bicycle tire at the gas station. The tire gets a little bit warm when it's fully compressed. Same thing happens in the cores of these clouds, only in this case, the temperature gets really, really, really warm to the point where nuclear fusion can occur, and then you have this formation of the star. The star typically has, the newly formed star typically has big bipolar outflow jets, and it's typically surrounded by a disk of material that you could think of as material left over from the star formation, a so-called circumstellar disk. And these circumstellar disks are of tremendous scientific interest because they are the birthplaces of planetary systems like our own. When stars form in these disks, as the star as the newly formed planet orbits the star, it sweeps up material in the disk to create this sculpted-like appearance. And here you have radio telescope imagery of these sculpted disks taken with a large radio telescope in Chile. This is a simulation of this process. And so one can see that by observing these circumstellar disks, we can infer the presence of planets without actually being able to see the planets themselves. And the JWST will do a great deal of work on circumstellar disks. Here are some examples. This is the disk around the star Fomalhaut, and this is Hubble's image of Fomalhaut and JWST's image of Fomalhaut. And you can see that in the JWST image, we have revealed all this inner structure of the disk that Hubble cannot see. And so the Webb will be doing lots and lots of work on disks like this. Here's yet another example. Here we have a circumstellar disk seen edge on. You can see that little black line there. And these big bipolar outflow jets are here. And I have this another here that made the cover of Nature just recently. So the Webb is really going to crack open a lot of new details on star formation and planet formation using its combination of infrared capability and ability to see fine detail. Here is another region of star formation close to the Earth, Rho Ophiuchus. It's pretty nearby, about 400 light years. And in this image, there are 50 new stars similar in mass to the sun. You can see one here has eroded out a big cavity, and you see a lot of shock-excited hydrocarbon emission. The Webb is really remarkable in the level of detail that it shows us. All right, this is an artist's rendition of the debris disk around our own star, the sun, alongside a map of where that debris actually exists. This debris are chunks of ice and rock left over from the formation of our solar system. And so as you can imagine, we really want to study that stuff. And so we put special non-sidereal tracking capability into the Webb telescope to allow it to observe these Kuiper Belt objects and also the outer planets of our own solar system. Okay, recently we, humanity, not JWST, got our first image of a Kuiper Belt object. Back in 2014, NASA's New Horizons mission was a Pluto flyby mission. When it finished the Pluto part of the mission, we sent it on to this Kuiper Belt object to take this first ever picture of one. And this is what we saw, and it was very surprising. It turned out to be two objects fuse together. And this simulation showed that it's possible for this fusing to occur as a result of a very low velocity collision, a few meters per second. The objects can fuse like that without either one being destroyed in the process. And this is of great interest to theories of planet formation, in which planets form by successive agglomeration of small particles into larger ones, producing a planet over 10 to the 8 years or so. So the JWST will be doing a lot of work on Kuiper Belt objects. Now, most of the liquid water in our solar system may not be on the Earth. Moons of Jupiter and Saturn are known now to contain vast oceans covered by a thick crust of ice. And as tidal forces act on that ice, the ice cracks and you get a geyser-like phenomena where the liquid from this ocean is ejected into space. And here's an actual image of that happening on Enceladus. This was taken with the Cassini spacecraft. Well, JWST is studying this ejecta spectroscopically. We have shown that it is water, and we've also shown that Enceladus is pumping out so much water that it's actually created a water ring that goes around the whole planet. And so really exciting stuff here. We'll see a lot more of this, but we will be able to understand the composition of this ejecta and the extent of this. And this is very important for the search for life. We know from studies of the mid-Atlantic ridge here on the Earth that one can have life existing completely disconnected from the sun on thermal chemical energy from those vents. And so a similar process could be happening here on Enceladus, and there may even be organic material on the surface of this ice. So this is going to be exciting research over the next couple of years. JWST has observed all of the planets that it can observe, and it will do that every year. And so over time, we will be able to see things changing that we otherwise would have been blind to. Here's JWST, a recent image of Jupiter. You can see aurora on the poles of Jupiter. It's the same phenomena as we have on the Earth. There's Jupiter's great red spot. This is a storm that's been raging on the surface of Jupiter for hundreds of years. Today it's shrinking. So JWST may help us understand why it's shrinking and why it's red. We still don't know why the great red spot is red. Here is an image of Uranus, where we now have revealed this rich ring system around Uranus. The Webb, with its infrared capability, is exquisitely sensitive to ice and rock. And so that's why it's able to see these rings so clearly. You see the rings around Jupiter and lots of small moons of Jupiter. All right, now when I was a graduate student, there were no planets known outside the solar system. Today, we've identified more than 5,000 planets, with the implication that there are tens of billions of habitable worlds in our galaxy alone. We don't know that they're inhabited, but we know that they're there, and we have learned how to search for life on them by studying their atmospheres. And the Webb will do quite a bit of this work. The search for extraterrestrial life is no longer the stuff of science fiction. It's very much a major science objective of NASA. So how do we do it? All right, we use a process called spectroscopy, in which we spread the light out into its component colors with special optics so that we can see emission and absorption of light by individual molecules and atoms in the gas. And we can actually identify what atoms and molecules are in the gas by the emission that we see. So here we have an example of spectra of Mars, Earth, and Venus. So what do we have here? A spectrum is a plot with brightness on the y-axis and wavelength on the x-axis. So in the Earth here, if the Earth had no atmosphere, this spectrum would be a flat line. It's not a flat line. It has all these bumps and wiggles in it, and all those bumps and wiggles are due to absorption and emission of light by atoms and molecules in the Earth's atmosphere, and we can actually identify all those atoms and molecules. And so what we're looking for in this process is chemistry that would be indicative of biological processes. That's the basic approach. So to get spectra of an exoplanet, of course, it's easier said than done. In the Webb, we'll be doing something called transit spectroscopy. As one can imagine, many of the exosolar systems that Webb will point at will be seen edge on. And so imagine we have the configuration shown in this cartoon where we have a star, we have its planet, and we have our telescope. And imagine that the planet is lying along the line of sight between our telescope and the star. We take a spectrum. What do we get? We get a spectrum of the planet's atmosphere plus the spectrum of the star. Now we wait a little while for the planet to move out of the way, repeat the measurement, that's just the star, subtract the two, and voila, we have a spectrum of the planet's atmosphere. Now I'm making it sound easy. It's actually profoundly difficult. The photometry that one has to do to make this work is parts per million precision photometry, but this has been turned into an exact science with the Hubble Space Telescope. And so the Webb, we know how to do this, and the Webb is already doing a lot of this. The Webb is primarily studying planets that are somewhat larger than the Earth. The Webb can detect water on an exoplanet that's a few times the size of the Earth. Now, if we're looking for extraterrestrial life, why do we care about water? It's not because alien life might get thirsty and need something to drink, but rather, in order for the organic chemistry of life to occur on a planetary scale, one needs to have a liquid solvent available on a planetary scale, and water is, what we're most familiar with. All right, so here are some examples of exoplanet atmosphere spectra taken with the process that I just described. So right off the bat, you can see something right away, that these are not a flat line. These planets have atmospheres. And we have, with the spectroscopy, we've actually identified a wide range of species in the atmosphere of this particular exoplanet, WASP-39b. We've seen methane, we've seen carbon dioxide, we see water, we see sulfur dioxide, which is very interesting because sulfur dioxide is indicative of photochemistry in the planet's atmosphere. So Webb is doing a great deal of this kind of work. We'll have to stay tuned, but there's already remarkable discoveries coming out of this. Here we've discovered lots of methane, lots of carbon dioxide, and possibly a molecule called dimethyl sulfide. This is not soup yet, this dimethyl sulfide discovery doesn't yet meet the exacting statistical standards that scientists use to claim a discovery. So it needs a little bit more observing time. But that dimethyl sulfide, at least on the Earth, that's only produced by biology. So watch this space, and we'll see what happens in the future here. Well, when we first put pencil to paper or marker to whiteboard on what kind of telescope we had to build to do that type of science, we realized that we needed 7 times the light gathering capacity of the Hubble Space Telescope. We needed Hubble's ability to see fine detail, angular resolution, as they call it. And we needed that in the infrared, which requires a very large mirror. And we needed observing capability spanning the optical to the mid-infrared. So when we realized those things, we then realized we had 2 enormous problems that almost stopped the project dead in its tracks. The first was that to get 7 times the light gathering capacity of the Hubble Space Telescope, we needed a mirror that was bigger in diameter than the biggest rocket. That was problem number 1. Problem number 2, to make an infrared telescope, the telescope has to be very cold. Why? Well, everything above absolute zero emits light. So if you had infrared goggles on right now, you would see the walls and floor of the room glowing in the infrared. Your body would be glowing in the infrared. If we didn't make the Webb telescope very, very cold, it would be blinded by its own infrared emission. Well, how cold do we have to make it? Really cold, almost minus 400 degrees Fahrenheit. And then and now, there is no refrigerator powerful enough to cool something as big as the Webb to such a low temperature. So that was the second problem that we had to solve. And, well, it's flying now, so you know we solved them. But let's talk about how we did it. All right, let's talk about the thermal problem first. The JWST was not placed in orbit about the Earth, the way most satellites are. We put it in a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And this point is 1 million miles away from Earth in the anti-Sun direction. Now, how does that help us cool the Webb? Well, as the Earth orbits the Sun, of course, this pattern of Lagrange points goes with it. And so one can see that if an object is placed at the L2 point, all the sources of heat on that object, the Sun, the Earth, and the Moon, will always lie in one direction. So then we realized, well, if we deploy a giant sun shield that would cause the telescope to always live in the shadow of the sun shield, then it will cool passively to the desired temperature by radiating its energy away to the cold darkness of space. Okay, so far, so good. But for this telescope to be useful, it has to be able to point all over the sky. So we designed the sun shield large enough so that the Webb could point 5 degrees toward the sun and 45 degrees away from the sun. We're still in the shadow. And now you can see that if we rotate the Webb about the Earth-Sun line, that's not going to spoil our shadow situation at all. And so now this arc turns into an annulus. And that annulus covers about 35% of the sky. So at any instant in time, the JWST can point at 35% of the sky and still be in the shadow of its sun shield. Now, as the Earth orbits the sun, we're rotating about this vertical axis, and one can see that this annulus will sweep over the whole sky every 6 months. So every 6 months, the JWST can point at any spot in the sky and still be in the shadow of its sun shield. And that's basically how we solved the cooling problem. Now, we didn't put the Webb exactly at the L2 point. We put it in a small orbit about the L2 point called a libration point orbit. It has a period of about 6 months. Why did we do that? Well, we did that. It takes about 2 kilowatts of electrical power to run the Webb. So we're generating that electrical power with solar rays, and so we have to stay out of the Earth's shadow. And so we put it in this little libration point orbit to keep it out of the Earth's shadow. This orbit is unstable in the direction of the Earth-Sun line, and so it has to be maintained with station-keeping thrusters. And the propellant on board for those station-keeping thrusters is modeled to last about 20 years. Now, another key feature of the L2 point that made it perfect for our mission was that an object placed at the L2 point, its distance to the Earth never changes, no matter how many times we orbit the sun. So the telecommunications range to the JWST remains constant no matter how long the mission lasts, and that's very important to our ability to get the data down by radio transmission. Okay, and that's just a little simulation of the libration point orbit. All right, so let's talk about that sun shield. The sun shield has an SPF of 1 million. So if you had this on the beach, you would be very well protected. It really is the size of a tennis court, 70 by 40 feet. It's made of a heat-resistant plastic-like material called Kapton. It consists of 5 layers. Each layer is thinner than a human hair. The sun-facing layer is coated with silicon, so it really does look pink in reality. The rest of them are coated with aluminum. It has 5 layers to get that SPF of 1 million. Each layer has to have a special curved shape. Those of you who sew realize that to make something curved out of flat cloth, you need a lot of seams. And each layer is a quilt of 50 pieces with about 7,000 inches of seaming. In this case, it's not done with needle and thread, but with thermal spot welds. Figuring out how to build this sun shield and deploying it in space was really the highest risk, one of the most difficult parts of the whole Webb mission. Here's an example of some testing on that sun shield. The sun shield here is folded up in a containment pallet. These mylar tables are there for gravity offloading. They're not there in space. but you see these telescoping booms, they are there in space. They pull the sun shield out of this containment pallet. You can see a person appearing in the center here. That gives you a sense of scale. And after it pulls it out of the pallet, these spreader bar assemblies around the periphery will spread out the 5 layers and also tension a cord that runs around the periphery of each layer to give it the final shape that it needs. And if you look closely, you can see the quilting here. Just an example of some of the kinds of testing that we do. All right, so the sun shield, why is it so risky? 140 release mechanisms, lots of hinge assemblies, 400 pulleys with as many meters of cabling. This was really, really complicated. It all worked perfectly. All of these things were single points of failure, yet we got permission to fly it anyway. And so, it all worked. But if you wondered what was the team worried about, this is what we were worried about. At least this is what I was worried about. All right, so that all worked fine for us. What about the big mirror? The mirror bigger in diameter than the biggest rocket. To solve that problem, we adopted something called a segmented mirror architecture. Instead of building one 6.5 meter monolithic mirror, we built 18 hexagonal segments that are mechanized to play together as if they were one big mirror. And that allowed us to fold the telescope up inside the fairing or nose cone of the rocket that we used. The rocket that we used was a French rocket called the Ariane 5, has a 5 meter diameter fairing, which is big enough to take the JWST. This is an end view, so you can see there's not much space left over in there, but we did fit it in there. This rocket is launched from French Guiana, Kourou Launch Center in French Guiana, which is on the east coast of South America. The payload was 6.5 metric tons, lots of deployments and release mechanisms. All right, the JWST mirror is not made of glass. It's made of a material called beryllium, which is a metal. Why did we use beryllium? Well, as the telescope slews around the sky to different objects, even though it's in the shadow of its sun shield, there will be small temperature gradients that form in the mirror. And we didn't want those temperature gradients to spoil the shape of the mirror. So we had to find a material that had a low coefficient of thermal expansion at this very low operating temperature of about 50 Kelvin or minus 400 degrees Fahrenheit. And it turns out that beryllium has that property. The beryllium starts out in a powder form, and then we compress it under tremendous heat and pressure to form a billet, and then a block of material. And then after we go through all the trouble to do that, we machine away almost all the beryllium. So this is the back side of a flight mirror, and this is the front side. You're seeing lab equipment reflected in the shiny side of the mirror. But you can see we remove all the beryllium that we can. So we're light-weighting this mirror as much as possible. Whenever one designs and builds something that flies, whether it's an airplane or a spacecraft, weight is a real engineering driver. And the Webb mirrors achieve an aerial density that's about 6 times lighter than the Hubble mirror, and they represent the current state of art for flight mirrors in terms of mass. Now, if you're paying attention, you'll realize that we have another big problem. How do we polish telescope mirrors? Well, we rub on them with gritty stuff until they become smooth and shiny enough. That's a room temperature operation. So if we're going to polish the mirror at room temperature and then use it at 50 Kelvin, it means that we have to put the wrong shape in at room temperature to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative process whereby we polish the mirrors part way and then put them in a specially instrumented space simulation chamber at Marshall Space Flight Center in Huntsville, Alabama, where we can cool the mirror segments down to their operating temperature, observe them with special optics test equipment to determine how our model is tracking to reality. then we would make corrections to the model, and we would iterate that process. So this is one of the reasons why it took so long to build the Webb, but this turned out to be very successful, and this is actual data here. So this is a flight mirror segment. This is at ambient temperature, and the colors denote relief, peaks and valleys, and we just take that mirror and cool it down. It all flattens out to a perfect mirror. So we had to achieve that for every segment on the telescope, and we did. All right, let's see. All right, after we got the mirror built and we got all the telescope optics integrated onto the telescope structure, and we got all the science instruments put on, the Webb was too big to fly in an aircraft. So the Webb has to be it kept very, very clean every time we move it from one place to another. So we developed this mobile clean room, if you will, a mobile shipping container. So the Webb telescope is in there, folded up, the way it will be folded up in the rocket. And this was too big to fly on any kind of transport aircraft. And so we decided to use a special roll-on, roll-off transport ship. And we shipped the Webb out of Seal Beach, California, just south of Los Angeles. We went through the Panama Canal over to French Guiana. This is the first time that NASA's delivered a payload by boat. It took us 2 weeks to get there. We had great weather, and this was an uneventful link of the chain. Then we got to French Guiana. Now, in French Guiana, here we're in the vertical assembly building in French Guiana. We're in an elevator riding up alongside the Ariane 5 rocket. There are work platforms set up in various stages on the rocket where people are getting the rocket ready to fly. We're going to the top. We're going to the top to see where the JWST is being integrated to the payload adapter of the rocket. And this is the very last view of the Webb telescope on the Earth. The spacecraft is fueled, and so that's why they're wearing these special safety suits. And here they're literally bolting the Webb onto the rocket, and then the fairing or nose cone is integrated axially like that. Now, when that's all done, the rocket goes out of the building on a crawler vehicle. It's really going very slow in real life. You could walk alongside it. And then we rolled it out there and launched it.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
All right. Yep. All right. So these are the first few deployments. First thing you saw was the solar array come out so that we could become power positive. We're operating on batteries up to that point. Then you saw the high gain antenna come out so that we could begin communicating with the Webb. And to get out to the L2 point, we did not orbit the Earth even once. We followed something called a direct transfer trajectory. One has to make a couple of trajectory correction maneuvers along the way, but the launch we got was so precise that those correction maneuvers were much smaller than expected, and that's why we have 20 years of propellant on board to do the mission. All right, this is how the telescope unfolds. The secondary mirror comes down like that. Various other radiators and things deploy at this point, and you can see the wings of the primary mirror unfold much like a round drop leaf kitchen table. All right, so we have to get those mechanisms to play together as if they were part of one mirror. So when we first point the JWST at a star, we have 18 separate telescopes. So first we have to figure out, we're going to get 18 images of that star. And when we have to figure out which image goes with which segment, so we move the segments one at a time to do that mapping. And then we will superpose, we'll adjust the segments to superpose all of those 18 images on top of each other. And then we use interferometric optics in one of our science instruments to adjust each segment to be coplanar to its neighbors to a small fraction of the wavelength of light being observed. And that results in a nearly perfect image. So the Webb, through this process, is exceeding its image quality requirements by about a factor of 2. So that all worked out for us. All right, so Webb is literally giving humanity its first high-definition view of the infrared universe. And here I'm showing what we mean by that. So these are our prior to infrared missions, WISE and Spitzer. The WISE, and this is 3 images of the same spot on the sky. So these 4 stars are these 4 stars are these 4 stars. This is Webb, Spitzer, and WISE. And you could see how much clearer the Webb image is. So what's the magic here? A telescope's ability to see fine detail is determined by the wavelength over the diameter of the telescope. WISE was 40 centimeters, Spitzer was 85 centimeters, and JW is 6.5 meters. And so here you're seeing the effect of that large mirror. And a lot of the Webb science comes out of its ability to see fine detail at the same level of Hubble. All right, so let's take a look at some results here. Remember, we said we wanted to see the first galaxies in the cosmic dark zone. Here, these are early release data showing that we are able to get those kinds of look-back times with JWST. Here, Z of 13. The universe is only a few hundred million years old at this point. We're able to do spectroscopy on very high Z galaxies to understand their composition. We haven't yet found a galaxy, free of metals, but stay tuned. This is really just getting started. A lot of surprises from the Webb's first view of the early universe. Shouldn't be a surprise. One of the surprises is that a lot of these very high redshift galaxies have very evolved morphologies or shapes. They have disks, they have spheroids. They're not irregular galaxies. And prior to launch, we kind of expected these early galaxies to be irregular. No, they apparently, these morphologies apparently evolve much faster than previously thought. Here's one of the cool results that is pretty recent from the Webb, where Webb data and Chandra data have been combined to reveal a very, very supermassive black hole at a very high redshift when the universe is only about 500 million years old. So a black hole of this mass, if the mass they're measuring is right, would have to be seeded to form in this short amount of time, would have to be seeded by something that is way more than is more massive than the kind of black holes that would be produced by supernova of the first stars. So some feel that this is evidence of black hole formation from direct collapse of primordial gas clouds. Stay tuned and watch this space over the next year or so, but I think the Webb will, pretty much revolutionize or at least invigorate all of our thinking about how galaxies form and evolve. Here we see, this is an interesting phenomena of galaxies being observed along the line of sight to a very distant quasar. So the quasar is like a giant flashlight, and it's showing this process whereby these very primeval galaxies begin to ionize out bubbles around in their environment that eventually grow and coalesce to produce today's transparent universe. This is imagery shows that process actually happening. Here's a stunning image of the Ring Nebula. The Ring Nebula is something called a planetary nebula. It has nothing to do with planets. A planetary nebula is what will happen to our sun when it runs out of fuel. The sun will throw off its remaining atmosphere to produce a nebula just like this. And this is Webb's image of this object, and it's stunning. You can see all this detail that we were never able to see before. You could see these successive rings that are occurring here. So the interpretation of this is going to take a while to figure out, but this is really stunning stuff. Here is a supernova remnant observed with the Webb. So this is what happens to a star that's much more massive than the sun. When it dies, it results in a giant explosion, some of the biggest explosions that occur in the universe, that leaves behind a remnant like this. This particular supernova occurred during recorded history, so people saw this as the appearance of a naked-eye star that wasn't there before. And this is where the heaviest elements in the universe are forged. You've heard people say we're star stuff. That is really true. The calcium in our bones, the iron in our blood, the gold and silver in our jewelry was made in a supernova explosion near the Earth. So this is really exciting new stuff that we're able to observe with the Webb. With Webb's ability to see fine detail, we see weird phenomena that we've never seen before. This is a remarkable image of a binary star, and you can see these successive rings of dust. This graphic is the interpretation of what's happening here, and it's fascinating, cool stuff. All right, so how does the universe work? How did we get here? Where are we going? And are we alone? Those were the central questions that drive NASA astrophysics. And the Webb mission enables the next step in humanity's quest to answer those questions. And you can join that quest. The people that do projects like this come from all walks of life, in all backgrounds. There's a quote that I like to read. The book of nature lies continuously open before our eyes, but it cannot be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures. That's as true today as it was 400 years ago when Galileo said it. So if you want to work in this kind of business, you guys are already in college, so stay there. Study whatever you love. But if that happens to include science, engineering, and math, then you should consider this kind of work as a completely realistic career objective. If you want to build spaceships when you grow up, you can do that. And if you want to find out what it's like, NASA has excellent intern programs for all levels of college, even high school, even postdocs, and you can have one-stop shopping for all those intern programs here. And let's say you want to really dig into some of this data that you saw, but you don't want to go through all the trouble to get a PhD and become a scientist. You can do that too. NASA has something called a citizen science program. And despite the name, you do not need to be a U.S. citizen to participate in that program. And they have a website. Okay, so those are places that you can go to further your interests. What's next? Well, we just launched the Euclid Space Telescope. That's a European mission on which NASA is a partner. And it was launched in July successfully. That mission is focused on understanding dark matter and dark energy, and it's working well. In 2024, the Vera Rubin Observatory will be commissioned. That's a giant ground-based telescope, and it is going to usher in a new type of astronomy called time domain astronomy, where the emphasis is on what's evolving with time on all kinds of time scales in the night sky. Then NASA's next strategic mission now that we've finished the Webb, will be the Roman Space Telescope. It's going to be launched in 2027, and it's focused on dark energy, and also a little bit of exoplanet imagery, light suppression technology. And then in the next decade, NASA has just recently got approval to do the Habitable Worlds Observer. So this will be a telescope the same size as the Webb, but it will be optimized for the UV optical spectrum, so it will be the true successor of the Hubble Space Telescope. And its main mission objective is to look at Earth-like planets and find those habitable worlds. All right, so those are my remarks for this afternoon, but I'm happy to answer questions for as long as they let me. Okay. No, it's fine. If you can update the internship website. Yeah. Okay, the website's up to date, and so if you're interested in an internship, you can just go right there and see what's available.
So one of the conversations that I've had a lot about love data that has been in the news and whatever is discovery of very, very early galaxies. You see all these sensationalized articles that are like, oh, and we just found out the universe is twice as old as it used to be, which is a bit of an exaggeration. But the last I was told is to wait for spectroscopic confirmation of those ages. Has that happened?
It's happening. Webb is our first mission to really be done in the era of social media. Okay, so there's a lot of stuff out there. The signal to noise is kind of low. You have to really pay attention to the source, okay? But, the Big Bang Theory is fine. The age of the universe is fine. Our understanding of how galaxies form and evolve, that is incomplete. We're seeing the early universe with this kind of detail for the first time. And so it's going to take a couple of years to begin to sort things out. But at this stage, you know how science works. It's very appropriate to ask, is that photometric redshift right? Is the mass right? You sort of question everything at this stage. And oh, no. It'll probably be within the next year, really, really quickly. And there's nothing is grossly wrong here. I mean, this stuff really is happening faster than we thought. Yeah.
I was just going to ask, in terms of thinking about future observatories, what would you say is like one of the biggest challenges? Maybe it's a managerial challenge or a technical challenge in terms of making this happen sort of on schedule and executed in the way that you desire?
Okay, well, right now, one of the biggest challenges is turmoil in Congress. Okay, we don't even have a budget. Okay, so that's a real big challenge. And cost is always a challenge. You have to realize that systems like this are expensive, and but in the case of the habitable worlds, we got approval with understanding that it really was going to be very expensive. Unlike the Webb, it came somewhat as a surprise at how difficult it was. So I think the future is very bright. All these systems that I showed will be realized, but we really need the turmoil in Congress to stop. Yeah. Go ahead. There is coordination. You'll have to, talk to the Institute to determine what the details are, but we very much want to enable Webb to work in concert with other concurrent facilities that are flying. So you've been trying to ask one for a couple there. Yeah.
Great talk. In your impressive engineered sun shield, because it's so thin, I imagine, and your rocket reed would just rip right through it. Do you have to worry about debris? And if you do,
Yeah.
so how do you engineer it?
Okay, so the Webb in anything that flies in space is constantly hit by micrometeorites. So that becomes part of the engineering problem. We have to design for that. So in the case of the sun shield, these micrometeorites, they won't penetrate more than one layer. And the velocities are so high that it's vaporized when it hits one layer. And so it's very unlikely that you would get a hole going through all 5 layers. And then the material that we chose has a ripstop feature to it. So if you poke a hole in, that hole can't be a source of propagation for larger failures. And the whole surface of the web, not the sun shield, has to be resilient to this. So right now, the way we're operating the web, we're keeping the shiny side of the mirror pointed away from the ram direction of the orbit to lower the closure velocity of any particles that might hit it. But so far, we're doing fine with micrometeoroids. Yeah. Say again, a little louder. Okay, I'm not sure. The primary mirror actually there are 3 optical prescriptions among the segments. So as you move out in radius, the prescription changes. But I'm not really.
Is that a product of the manufacturing process? Does each segment have to be treated separately, and the different definitions apply to each segment?
Well, each segment is manufactured separately. Maybe come down afterwards, and maybe we could look at what you saw, and we'll talk about it.
That was an amazing talk. Thank you. My question is, how do you decide on the range, the spectral range that you will be capturing for the next?
Okay.
You can have it all. Why not?
Yeah. How do you make these decisions? Well, first of all, you can't have it all. Okay, the detectors that we use don't respond, panchromatically. So when building a system like this, you do have to decide what those limits are going to be. It's a science decision, right? There's a whole community of scientists that are terribly disappointed that we stopped at 28.5 microns instead of 29.5 microns. And same on the other end. So ultimately, you have to make science-based decisions. And so very early in the Webb mission, we pulled in competitively selected science working groups that were drawn from the whole astronomical community to have committees come in and discuss this and eventually make the decision that, what those endpoints are going to be and what all the science features of the observatory is going to be. And that's generally how we do it. So the Habitable Worlds Observer, the one that's going to happen in the next decade, that process is going on right now. They just selected their first, interim science working group to begin doping out the broad brushstrokes of what that observatory is going to do. Yep.
Do you have any expectations in terms of things that you hope to see in the known universe in regards to like space biology and life with this?
Well, yeah, that's those exoplanet spectra are, very much about biology and so forth. And it's going to take the case for life is going to require lots and lots of evidence because it's such a big deal. So one biomarker, one indicator is not enough. All right. So the Webb, if we find tantalizing biomarkers in some exoplanet, it'll probably be multi-mission follow-up of that before we finally start the chest thumping that we've discovered life. Okay, but yeah, so there.
Webb is, in terms of the search for life, is mainly focused on the spectroscopic approach.
Yes, exactly, and there are umpteen, models about, what we might see. Yeah. Yeah.
When you think about upcoming projects at NASA, like the ones that you discussed in your talk, what types of professionals do you feel like are in the highest demand right now?
What is what?
Like what types of professionals do you feel like are in the highest demand
Oh, what type of professionals? For using the Webb or building the Webb? Okay. Exoplanets, that branch of astronomy is brand new and it's exploding all around us. It's in explosive growth. And so, a young astronomer going into exoplanets, you're probably going to find a lot of fertile ground there. And then on the engineering side, every branch of engineering that you can possibly think of is actually involved in things like this. And so my advice there is just go with what you love. At the end of the day, it's important that you love your work because you spend most of your life doing it, so you might as well love it, right? Yep. Yep.
In the captured images of our solar system planets, don't you worry about the relative intensity? Because aren't they very bright since how close they are? Do you not need to worry about that?
Worry about the brightness of the solar system planets? Oh yeah, absolutely. There are objects in the solar system that the Webb can't look at, and in particular, we can't look very close to the sun. So we can't look at planets inside of Mars, and yeah, you can overload the system. So we have control of what the spectral bandwidth is, and so you have to make an appropriate choice for the object that you're looking at. Yeah.
Yeah, thank you so much for the talk, by the way.
Yeah.
When it comes to continued operation and maintenance of JWST, obviously you can't send a technician out to L2
Right.
to fix anything, but what kind of remote analysis and possible fixing of things?
Okay. There's no servicing at L2. The astronauts can't go to L2. Okay, so we had to live under that sort of Damocles, if you will, that we knew that if we didn't get it right, there's no way to fix it. Okay, so that's just a reality. We could do a propellant replenishment mission on the Webb, just propellant. There's no plan for that. And who knows if that'll ever happen because we have 20 years of propellant on board. And 20 years is a long time for something to be in space. So the Webb most likely will not be serviced. However, everything else that we build is required by law to be serviceable. The Webb wasn't. And so like the Roman Space Telescope and so forth will be fully modular and able to be serviced. Now, that said, we diagnose and fix little problems on the Webb and on Hubble and all our systems in flight all the time. And, we have engineering processes for doing that. The toughest part of fixing things in flight is we've learned that it's important to determine what's broken before you fix it. Okay, and so it's called finding the root cause of whatever the problem is. We normally use the Ishikawa method to do that. Sometimes that's called fishbone analysis that you might have run into in some of your engineering classes. But we have systematic procedures for diagnosing the root cause of a problem, and then if we've done our jobs right, we can often have the adjustability to mitigate whatever's going wrong. Yeah. Either one. Okay.
Thank you for a great talk.
Yep.
For all the work you've led on this project. My question was about the observation of more symmetrically mature galaxies in earlier galaxies than was hypothesized. So how does that inform where you might be looking temporally, right, for those deformations to have occurred? And how would you program that into your future spectra probes?
Yeah. All right. So, the morphology of the early galaxies is somewhat of a surprise. Okay. So it's going to take a little while to figure that out. You're going to figure it out, not us. So every year, NASA solicits observing proposals from the worldwide astronomical community. People send in their ideas. Those proposals are peer-reviewed, reviewed by other astronomers, and some are selected. We've just solicited the third round of annual proposals. We got 2,000 proposals back, which is considered a lot, and we'll probably get more. Now, NASA, one thing that's new on the Webb in this process is that NASA has gone to a double-blind proposal evaluation system. So that is turning out to be a huge advantage to young people and women astronomers. And so it's a great time to be proposing. And if you have any kind of an idea, don't hesitate for a moment to write a proposal. Don't think that, because I'm a graduate student, nobody knows my name, I don't have a chance. That's not true. It's double blind. And so, you will solve those problems, not us. Yeah, you had your hand up.
How are we going to get it back from there?
No, we're not going to get it back. We have 20 years of station-keeping propellant. When that propellant is exhausted, the Webb will fall out of that little libration point orbit and be left in a generalized sun-centered orbit forever.
Will you still be able to get information back?
No. Well, we could talk to it for a while, but it won't be able to do science, and we'll probably be told to turn off the command receiver so that it can never be spoken to again. That's what we do nowadays to prevent a bad actor from, hacking into an old satellite, bringing it back to life, and doing nefarious things with it. Yeah. Yeah. I don't have a suggested candidate for that. But we're looking for exoplanet environments that are, like the Earth. So you'll hear people talk about the habitable zone, where water can be liquid. And our understanding about how life can arise, you need water, you need a rocky surface, so you can get elements from that rocky surface. We need a magnetic field so that the surface of the exoplanet is not impinged with radiation. That would be difficult for life and so forth. And so we can want these things, but we have to go look for them. And so the Webb is going to observe lots and lots and lots of exoplanets every year. And we'll see how it goes. But many of the most interesting molecules have their features in the passband of the Webb telescope. That's not an accident. And so it should be very interesting as time goes by. Yeah.
When you're building and designing for a project that is going to be this many years long, how do you design in the idea, knowledge that technology is going to be changing, and that the detectors that you maybe started off thinking you were going to use 10 years ago are so inefficient? So how does one design a project knowing that by the time you get to where you need it, the technology?
Yeah, it's a good question. The technology on everything that's flying is way behind the actual state of art. So the project going from idea to, we're sitting on the pad ready to launch, that's broken up into specific phases. And there are certain things that each phase has an entrance criteria and an exit criteria to get out of it to the next phase. So right in the very beginning, one has to show that all of the technologies that are needed by the mission are at a certain level of readiness. And that happens very early in this flow. And then that technology is frozen. So no matter what wonderful things are happening while we're building this thing, the technology is frozen at that point. And, that's basically how we do it. Yep.
Do you have a sense of how much of the sky would James Webb Space Telescope get to look at across its lifetime?
Oh, we get to look at the whole sky. The Webb can point at any spot in the sky every 6 months.
Yes, it can point to any point, but it takes some time in order to look at a region. You then need to go to another one.
Yeah.
So I'm thinking, like, across its lifetime, could it get to look at everything, or it just takes too long to look at a small spot, and there's not enough time for it to look at everything?
Well, I don't know if it'll. We're not going to map the whole sky. But there are missions that do that. There's a mission called SphereX that is going to provide near-infrared spectra of the entire sky. But that's where we are. The Webb has a very narrow field of view. The missions that map the whole sky, they typically have very broad field of view for obvious reasons. But if we imagine, if we made a map of every place that the Webb pointed at the end of the Webb mission, what would it look like? It would probably look like Hubble, I would imagine.
How large is that?
Pardon?
How large is that?
Hubble is a 90-inch telescope, basically. Yeah.
No, I mean the view of the sky that Hubble got.
Hubble hasn't observed the whole sky, but it's going to spend more time observing, say, in the galactic plane, because that's where all the stars are. So if you had a map of every place that, if you took the whole sky and put a dot on it, every place that Hubble pointed, it wouldn't cover the whole sky. It would cover all the places that people thought there was something interesting going on. And I imagine that the Webb at the end of its mission, that pattern would probably look similar to Hubble. I don't know. Yep.
Just a follow-up.
Yeah.
Where is the future? Sorry,
Yeah.
What's next for where you will be focusing the telescope? Are there specific regions of interest that you'll be probing outside of the ones that you plan to return to each year?
Okay. Again, we go out to the astronomical community, collect all these projects that are approved. Okay, and then once they're approved, we have this big basket of approved stuff. Okay, so now we have to schedule that in an efficient way. So, and that's a big problem because there are all kinds of constraints on how that scheduling is done. And so if you have an observation that's been approved, it might take a long time for that to come up in the schedule, depending on where it is. But taking that basket of approved proposals and figuring out how to schedule it efficiently, that's another big, hard technology problem. It's one that we solved and we're working. Yeah.
Is there anything in the very near future, just as like an example, a specific example of something that people are probing for interest? It's okay if
Well, there is a point on our website, I don't have the link here, where you can look at what's coming up. It shows you what's coming up in the Webb schedule, and that's open to anybody to look at. And so you can see if your favorite object is coming up and what's going to happen with it.
I'm sure there are a lot more questions. We should thank our speaker again.
All right.
If you want to come down and ask questions after this, that's fine.
Hi. Sure.
I'm a master student here.
Pardon?
I'm a master student.
Okay.
And I'm graduating next year. I would like to know if there's an opportunity that I can work for NASA.
Well, as a master, you can do an internship.
Yeah.
So that's like a summer job. But all NASA jobs are advertised in one place called USA Jobs.
Yeah.
Okay? And so if you're interested in working for NASA or NSF or DOE, USA Jobs is one-stop shopping. And that's the place you can set search items there so that you get alerts back for whatever you're looking for. That's
Thank
what.
you.
Yep. Hi.
Thank you so much for the talk, first of all.
Yeah.
It's fascinating.
Yeah.
I was wondering,